Okay, now that our geometry is defined, we can run an analysis, and this is done in a very similar way to the foil analysis. So let's switch to the polar view and show the four graphs that we need. First thing to do is to define an analysis. Type 1, 2 and 4 are the same as for the foil analysis. Type 5 is used to evaluate the effect of slight slip. Let's use a type 2. This is the most interesting type of analysis. It means that for each angle of attack, the program will adjust the velocity of the plane so that the overall lift is exactly matching its weight. This gives us a good feeling of steady level flight, which is a good optimization point for our plane. To analyze this plane, we'll use either VLM1 or VLM2. These are two methods which I implemented to see if there was a difference. There is none, except that VLM2 is usually more stable, so I recommend VLM2. We took the precaution to generate the viscous properties for each foil, which means we can activate the viscous checkbox here, and we will leave out the tilt geometry option. We have also predefined the plane inertia, so we can use it. Otherwise, we would have to enter manually the values here. And we'll leave the other parameters unchanged at this stage. Okay. So this analysis, its name appears in this list box here. We've only got one at this stage. And we're good to run the analysis. Here we go. Everything seems to have gone well. Nonetheless, if we want to check, we can view the log file or type L, and well, it tells us that for the first AOAs the program found a negative lift, which means well, the plane is just not flying, it's diving, and it can't find velocity to balance the weight of the plane, of course. So starting from an angle of attack of 0, the plane starts to fly, and at 0 degrees of AOA it needs to fly very fast for horizontal flight, because the lift coefficient is quite low. Okay, let's go on, and all the points other than that were calculated all right. Let's see how it looks in the 3D view. Well, we don't need the masses anymore. In green, we have the lift line. This is the lift which is acting along the span of the wings. If we look at low AOA, well, we have more lift on the wing, but we have downwards lift on the elevator. That's for stability. If we look at high AOAs, we find that they are both lifting, and this will induce a pitching moment which will tend to bring our plane back to horizontal attitude, which is good. We can look at pressure coefficients. Okay. We can look at the drag, induced drag and viscous drag. As I mentioned, they are the same order of magnitude, which means we can't neglect either. We can look at the transitions, and this is the place where the flow is going to transform from laminar to turbulent on the top surface and on the bottom surface. So at 10 degrees AOA, the flow will be changing its nature at this position on the upper surface, and it will be laminar up to the trailing edge on the bottom surface, which makes sense. We can look, interesting thing to look at is the streamlines behind the plane, and if we look at it from the exact rear view, we can see that we have these two tip vortices at the extremity of the wing, and this is a nuisance. All the energy that is used to generate these vortices is lost. It is not used to sustain the plane. So a big part of the plane optimization is to reduce these vortices, and you can use this view to find out how these vortices change with your design. And one thing of interest here is to put some winglets, which are specially meant to reduce or eliminate the vortices. If we wish, we can perform an animation. It's always interesting to see how this changes with AOA. Increase the speed a bit. So as we reduce the AOA, we get less tip vortice, and as we increase the AOA here, we get more and more tip vortice and more drag. Okay. One thing to remember is that the energy lost in these tip vortices is exactly the work of the induced drag. The induced drag is the force corresponding to the energy which is lost in these tip vortices. So when optimizing one, you automatically optimize the other.